This is Sung, and I'm the Principal and Director of Sky Academy. And in this episode, what we're going to be doing is continuing our journey through basic arithmetic of real numbers, and we're up to the stage now when we're dealing with rational and irrational numbers in particular. So irrational numbers meaning numbers that involve root signs, okay, either the square root or the cube root or etc. Okay, and what I want to do is show you, okay, that numbers that have root signs, square root or cube root or whatever root, are irrational. Okay, obviously the ones that become the square root of a perfect square or the cube root of a perfect cube is going to be a rational number. It's going to be a whole number, okay, or a rational number. Other than that, most surds are going to be irrational, right? And the square root of 2 is a classic irrational number. And what I want to do in this episode is to show you a neat little proof that really goes back to the ancient Greeks, who realized that the square root of 2 is an irrational number. And the way that they proved this was by a method called proof by contradiction. So what they did was they basically started out with the premise that they tried to disprove. So assuming that the square root of 2 is rational, they then manipulated things to show that it couldn't possibly be rational because it doesn't fit if we were to assume that it is rational, okay? And that method of proof is called proof by contradiction. By assuming that it is rational, it contradicts itself, okay? And so therefore, root 2 must be irrational. And that's the proof that we're going to go through. And so this is how it goes. The question is the square root of 2 a rational number? And the proof is, let's assume root 2 is rational, i.e. root 2 is an element of the rational numbers, okay? So let's assume that the root 2 is rational. That means let the square root of 2 equal a on b, where a and b are natural numbers without common factors except 1. A and b are natural numbers without any common factors. So if there were common factors, then you can simplify a and b down to other smaller numbers, which would then not be a and b. Does that make sense? So it's very important, and this is where the proof, the crux of the proof is that a and b have to be to the simplified to the lowest terms. A over b must be simplified to the lowest terms. So let the square root of root 2 equal a over b, which means square root of 2b is equal to a. So b times the square root of 2 is equal to a. So square both sides, which means that 2b squared is equal to a squared, which means therefore a squared is an even number, which means if a squared is an even number, the square root of a squared must also be even, okay? Which means that a is also an even number, i.e. a is equal to, say, 2k, 2 times another number, say k, which would mean 2b squared is equal to 2k squared. Does that make sense? Now, if that's the case, 2b squared is equal to 4k squared, b squared is equal to 2k squared. Now, the thing here is that k is a counting number, a is a counting number, and b is a counting number, which means b squared is an even number also, and so is b, right? So b is an even number, a is an even number, but they can't both be even, because if they're both even, then a over b would not be simplified to its lowest terms. They have a common factor of 2. So, but B and A can't both be even, therefore the square root of 2 cannot be a rational number. Because if A and B are both even, and here we've proved that they have to be both even, then A over B cannot be a rational number because there will be some factor that can simplify A and B down to smaller numbers, but those smaller numbers won't be A and B, and those smaller numbers will also have to be even as well, and it'll keep going on forever where you can't cancel it down. Therefore, the square root of 2 cannot be a rational number. It must be an irrational number, cannot be rational. Thank you very much for watching.